So Kristen came to us from Notre Dame, where she was a star student. Every time I meet the faculty at Notre Dame, they always ask me how she's doing. So the great thing, so she came and she started working with me and was working in cognitive radio. And the great thing which you'll see through Kristen's talk is that Kristen not only can sort of hack all the math, she can also crunch her way through 100-page law review articles to understand what these people are arguing about from a philosophical point of view, so we can begin to understand it and model it. So you'll see the fruits, the tip of the iceberg of the fruits of that in this dissertation.
Thank you very much. So yes, today we're going to talk about building trust into light-handed regulations for cognitive radio. So I shouldn't have to tell anybody in this room that wireless use is booming. So this is a graph that was put together by Cisco to look at how much data we're sending wirelessly in the next few years. And you should notice first that it's exponential, and second that this is in exabytes, which is billions of gigabytes. So, I mean, we have all of this need for new spectrum in the next coming years. And at the same time, the government is realizing that we need this too. We need this kind of connectivity and the internet, really. So they put together this national broadband plan that's trying to get internet to everyone in the country. And they think this is going to require 500 megahertz in the next 10 years. Now we have all of this demand, but we have really no spectrum. The last time spectrum was actually available was in 2008, and it was around 66 megahertz, and it sold for $20 billion. So, I mean, lots of use, billions of dollars, we need more spectrum. And to understand why there isn't any spectrum, you really have to understand how the FCC does spectrum allocation. So let's look at that. If you look at a wireless signal, it has some bandwidth and frequency. The power drops off over space. You can turn it on and off in time. And if you're the FCC looking at this, you say, I need to find a piece of spectrum for this wireless signal to live in. And I'm going to give it an allocation, which is really a box that this spectrum, that this wireless signal is going to exist in time, space, and frequency. Now, this box really needs to be designed for this network to run in it for a long time. So these boxes are huge. In time, they're decades long. Frequency, megahertz, and space, 1,000 kilometers squared-ish is the smallest, which is about the size of a city, goes to nationwide. So I mean, these allocations are really, really big. And if you're a network designer, to actually deploy a system, you need to get your box. You need to prove that your devices are going to respect your box, which is FCC certification, and that's going to be very important. And then you can actually deploy your network. So the FCC creates all of these boxes and kind of stacks them up with a little bit of guard band and space in between so that you don't have interference coming from these boxes into any of the others. And building these boxes up is how you get this frequency allocation chart. This is the frequency allocation chart for the US, and it shows only the frequency dimension of these boxes. Time lasts for decades, so it's not all that interesting. And space, they're again really big, so it's not going to be shown. It's just frequency. So looking at this, everything is allocated. But if you look at how much is actually used at any given place at any given time, you get something that is like this. This is a plot done at BWRC back in 2003. And time is in minutes along the bottom. Frequency is along the side. All of the green spaces are unused. All of the orange spaces are used. So, I mean, if you look at this and you think, wow, there's a lot of spectrum out there. About 95% of spectrum is unused on average in any given place at any given time. And all of this unused spectrum we call white space. Cognitive radio is trying to figure out how to use that white space. And it's happening right now. So in 2008, the FCC allowed white space devices in the TV bands. And in 2012, PCAST report came out, which has White House and FCC support to extend cognitive radio and spectrum sharing into other bands, like the federal bands. Because they realized that to do the National Broadband Plan, you don't need 500 megahertz, you need gigahertz. You need a lot of spectrum to make this happen. Okay, now, to understand what's going on in this talk, we're going to look at the TV bands. So what's the problem there? You have a TV tower. This TV tower is surrounded by TVs, and they're all inside some region, which we're going to call the protected region. Now, all of this space outside is unused. We need to figure out how to put cognitive devices there. And so we put in this guard space. You remember the guard space from the allocation boxes. And this is called the no-talk region. And outside of there, you can put your cognitive devices. Now in the TV bands, you can do this in two ways. Under a database rule, where your cognitive device sends a GPS signal to a database. This is going to be fun. GPS signal to the database, which sends back a list of the available channels. And the cognitive device can operate in any of these available channels. That's one rule. You can also use a sensing rule. And in this rule, every cognitive device can listen to the TV and say, is the signal quiet enough? Less than this minus 114 dBm, which is really small, by the way. And if that's true, it says, yep, I'm good, I can transmit. So how much white space is actually available? Under the database rule, you get this top plot. And this was done by Mubarak a while back. TV channels, these are numbers of TV channels. And under the database rule, there is a ton of white spaces available, just everywhere. But this is what happens with your sensing rule. All of your white spaces collapse. So why does this happen? Under the database rule, you can set this no-talk region and have somebody come in. And it's very easy to set and distribute. But the sensing rule, you're essentially worried about this case. This cognitive device is sitting behind a building, which is between it and the TV. So it can't hear the TV. And you want to make sure the receivers are protected here. But that means that you have to make your sensitivity really, really low, so any device that doesn't have that building doesn't see this radius, it sees this one, and your white spaces are gone. Now, technology can fix this. Instead of having a per node sensing rule, you can have a network sensing rule. And these guys together can say, yep, we're good, we can sense. Now, the problem is, how do you trust that? How are you going to prove that your sensing rule is good? Using a certification test that is every single device. I mean, you're going to have some collective emergent behavior coming out of this. How are you going to certify that? How do you trust that? Moving even away from this, there are so many new technologies coming out of academia that could solve this finding spectrum holes problem. I mean, beamforming, interference alignment, any of this, if you actually want to do it, you need to prove to the FCC that it's going to do what it's supposed to. Now, even if you could, that process of certification requires like 10 years. And it's really opaque whether you can go in from the beginning and actually deploy at the end. I mean, this isn't something that you really want to have to do all the time. And this is what we're doing, this develop tech, develop certification requirement, deploy, repeat. We don't want to do this anymore. I mean, there's another option that says just have everything be LTE, which is a cell phone protocol, and all devices run LTE, they will rule the world. But again, it's going to be really hard to get anything added to LTE. You really want your new technologies to be deployable without this bottleneck of certification. So really what we want is this path of freedom that says, let's separate the requirements for certification from your device technology. Now, at first glance, this seems really hard, right? If I'm going to prove that my device does what it's supposed to, how can I do that without showing you what my device does? that's really the problem that we want to solve. And in the spectrum sharing area, there really isn't any technical solution to this problem yet. Not before my thesis. Before my thesis, you had to go look at policy literature, which really means you go look in the law journals. Now, these guys talk about everything policy related to cognitive radio. Absolutely everything. There's a ton of ideas in here. I mean, there are things like real-time markets will figure it out. Don't worry. Privatization will help. But you're just moving the problem. You're not solving the trust problem. You're handing it from the government over to the private folks. So we still need to do it, which is the same problem with pricing as it's applied to cognitive radio these days. It's about sending, giving allocations to people and not about trusting that that's going to happen right. You can have limited rules and let the best sharing technology win, which is essentially saying don't trust anyone. Just let them fight it out. That's not okay either. These go together in what you want to do with spectrum. Is it unlicensed? Is it commons? Is it licensed? And again, any of these, you're going to have to trust them somehow, which relates to property rights, how you say what you're going to do and what you're not going to do. And we really want what you're not going to do, but we don't really know how to define that. If something goes wrong, you send it through the courts or through spectrum tribunals, and spectrum tribunals are kind of like patent courts, and we know how well patent courts work. So, and for any of that, we need identity. Identity is key, but that's all we know. So, I mean, there's a lot of really great ideas in here, but you can't build a system off of this. You need this to be translated from all of these words. You don't know what's important. You have no idea what is the equivalent of SNR in enforcement, in trust. You know how to build a wireless system on SNR. We don't even know where to start. And that's really the contribution of this thesis. This thesis looks at all of this, distills it all out, puts together a mathematical model that can start answering these questions. What are you going to do? How do you give trust? How do you create a do not harm rule? Can you enforce it? Can you create this system that can guarantee trust without requiring a certification of the technology of the spectrum access technology? And then you can answer other questions. What components does it require? What's the hardest cases to ensure trust? What are the performance metrics? How does it do? How does this improve over time? What are the important parameters for defining this system? That's what we're going to do. So the rest of this talk, after lots of introduction, the rest of this talk is going to be about modeling, about creating simple models to get out important parameters. So we're going to look at regulation as a system design and look at a hierarchical control model that shows you why this hinges on trust. Then we're going to look at spectrum jails as a way to ensure trust first and have certification rely on that, and then let performance evolve later. And this is a utility maximization mechanism design model. And we're going to ask which role the primary should play in its protection, which is modeled as a Stackelberg game. We're not really going to have any time for it, but it is in my thesis, looking at multiple secondaries and aggregate interference. And for that, bring in some stochastic geometry and some queuing to really take care of that case. And I do want to have a little bit of time at the end to look at what we've accomplished in this thesis. Okay, great. So as an engineer, looking at the problem of spectrum access and cognitive radio, really you're operating here. You have a wireless device, you're trying to access local spectrum, and this is your control problem. You have a lot of information. You can have information through the database, you can have local context, but the technology, literature and work is, in cognitive radio is really looking at this. There are hundreds of papers on this. This control problem, where you're really trying to control noise, you're trying to control the uncertainty from other devices, looking for these spectrum holes. Now the problem of regulation is different. The problem of regulation is not what can you do, it is what will you do, and what will you not do. So from a regulation perspective, this is your plan and your control problem, this whole system. Because you're trying to control temptation. You're trying to control the temptation of building a wireless device that's going to stomp on everybody else just to do what it wants and get more utility for itself. And the FCC has two tools to work with this. It has certification that can lock down technical components of this device, which is what the FCC does now. It relies entirely on certification. And what that does is make sure that all of your trust problems are running kind of as an open loop control problem. You have to make sure these things are stable at the beginning, and it's extremely inefficient. If you want that efficiency, you need to be able to let this be unstable, but luckily there's a controller in there, a controller through an enforcement system. So I'm going to move these around to look at what this enforcement system looks like now. Your wireless device is down here. This is operating on the network operation time scale, which is milliseconds to minutes. If something goes wrong, the affected network administrator realizes this goes wrong, complains to the FCC. The FCC investigates with a band with a directional antenna, finds what goes wrong, issues a cease and desist order to the device owner, who removes the device. This operates at the human timescale, which is like weeks to years. And making sure all of this deploys right at the beginning is the FCC certification. This runs a device lifetime. Now, when the FCC moved to allowing TV whitespace devices, what changed? They added a database. That's it. This database that gives information here on local context. They didn't change this enforcement system at all. Now, what happens when something goes wrong? What if there is a device that malfunctions? What are you going to do? Are you going to wait for the complaint to go all the way through this human enforcement system? You really don't want to. At the very least, you want to let the FCC cut people off of the database, right? I mean, the database is right there, waiting for this. So why don't we do that? Give the database a kill switch. Let it control a little bit. But, I mean, now you still have to wait for these complaints. Database could do that too. Give it the ability to see identity. And this kill switch, and now you really don't need this enforcement system at the human level. You can leave some of it up there, but really what you want is a spectrum manager, an enforcer that operates closer to runtime, so it can actually deal with these malfunctioning devices. So we have this kill switch and identity at runtime, but we still have this database controlling what frequency bands devices are allowed to access. Is that a good idea? And it really depends on what you mean by a band is occupied. Because if you have database time slots, and a primary comes in and uses 25% of the band and it looks like this, then this is great. The database can send the rest of them to connative devices and we're good. But what if it looks like this? Now we've got a problem. Because now no slots are available. The database can't, it can only send that this slot is available if there's no primary there, and it can't do it. The database can't actually get this piece, but maybe a local connative radio can. If we look at this in plot form, down here is the primary time slots per database token and band utilization. The primary is going to use 30% of the band. The database by itself can recover this many spectrum holes. As soon as it's an order of magnitude off, here, you are getting almost nothing. A database really isn't good enough if you can't run that database at the same time scale as your spectrum holes. But again, maybe local decisions can. So we want to use this kill switch and this identity system to trust local decisions. And the question is, can you do it? And the answer is yes. And this is using really a folk theory, it's this relying on a folk theorem about repeated games that says these cognitive radios are around for a really long time. So this really is operating as a repeated game. And you can keep them honest if there is a credible threat of being able to do something to them if they do something wrong. That's really what it's all about. So we're worried about this case. Lots of interference from cognitive devices over there to our primaries. And we're going to put this database in the middle. Now, this is a real conceptual shift from how people think about these databases. Because the cognitive device is requesting a token, but the token that the database gives them is not a token that says, you must use this band. It's a token that says, yes, you may now access Spectrum, but you are responsible for finding an open band. You are responsible for respecting the primary and figuring out all of that. And if you do something wrong, your token is going to be revoked. And this revoking a token and making them stop operating, that's what we call a spectrum jail. So, how are we going to model this? Because really this is about mechanism design, understanding that token revocation process, and deciding how long you're going to have to wait until I give you another token. So let's say we have a primary band. We have a primary that has some on-off characteristic. We're going to model it as a Markov chain. But the important parameter here is how often the primary is around, a probability of transmitting. If the primary is not there, the secondary can legally transmit, or it might have a false alarm, but for our purposes here, we're going to ignore that and just assume that it knows where the primary is if it looks. And it has costs associated with this. If it's legally transmitting, there's some transmit cost. Whenever it looks for the primary, there's a sensing cost. Now, if the primary is transmitting, the secondary can choose one of two things. It can either cheat and transmit anyway and then cause interference, or it can not cheat and wait for the primary to go away. Now, in either of these two states, there's a probability of going to jail. If you're cheating, it's the probability you get caught. If you're not cheating, it's the probability that you are wrongfully convicted. Once in jail, you stay there for a certain amount of time, and it's this certain amount of time that we want to design and figure out what we need to do with. So what do we want? We want to enforce the do no harm rule. We want to make them not cheat. We want to guarantee trust first and performance later. We want to know what technical components this requires, beyond the kill switch and the identity that we already have. And what are the hardest cases in which to ensure trust? What are the performance metrics? And what are the important parameters? So that's what we're going to look at. First, can we enforce this do no harm rule? And you would think yes, right? This should be possible. So this model is really very simple. And all of the math is going to be in the thesis. To have you actually understand what's going on, I'm going to show you a bunch of pictures instead of the equations. So we're going to do it like this. The secondary options are going to be along the bottom. The cost is going to be up this side. So the secondary can either cheat or be honest. There's some cost for this. There's a transmit cost. And you're going to spend a little bit more transmitting if you're honest, because you have to wait for the primary. If you're honest, you have to sense. If you're cheating, you can go to jail and have a sanction. If you're honest, you can go to jail and have a sanction there too. And in this case, yay, we win. You're not going to cheat, because your cost is lower if you don't. So this is great, right? But can we guarantee trust first and performance later? Now, this is a little questionable, right? Because we have this sanction box. We're really comparing it to the sensing cost. If that sensing cost gets bigger, secondaries are going to cheat. And this seems to rely very much on that sensing cost. But the thing is that cognitive radios are frequency agile and intelligent. If it costs that much for them to look for the primary, they're really not going to do it. They're going to operate somewhere else. They're going to operate in an unlicensed band. So we add a home band to capture that effect. And now look at what we've done. With this home band, your sanction needs to depend on how big that home band is. That's your choice. It always must be cheaper to go there than to cheat. And it doesn't matter on this, the sensing cost doesn't matter anymore. So yes, as long as this sanction is based on the size of an unlicensed band, we can guarantee trust first and performance later. So now we can ask these other questions. What is the hardest case to ensure trust? If we look back at this figure, how are we deciding this sanction? Yes, it depends on this transmit cost, but it also depends on how often the primary is around, this PTX. Because we're enforcing this do no harm rule. You're never going to get caught doing harm if the primary never transmits. So if that PTX gets smaller, those secondaries are going to cheat. They're going to cheat based on how big that sensing cost is. Now, I know what you're saying. You can just make the sanction bigger. This should be fine. So if you make that bigger, you can do it. But then PTX goes down again, and you're cheating again. So you make it bigger again, but when you make this bigger, you're making this wrongful sanction bigger too. Which means as you're making this bigger, you're sending more of these cognitive devices over to the unlicensed band when they could have been getting these spectrum holes. So you don't want to do this.
Yes. Why is
Yes.
the wrongful and the rightful sanction, why are they different? I mean, here it shows the cost is different.
Yes.
I would think a wrongful sanction, as far as the jail is concerned, is the same as a rightful sanction. It's the
Yes.
same.
So the size of the jail sentence is exactly the same, but your probability of going there is different.
Oh, so this is expected cost.
This is expected cost. Okay, so this low PTX regime is going to be a problem, and you need to do something about it. Really what you do is choose. There is a minimum transfer probability that you're going to protect. And below that, we have a use it or use it rule. The primary is not going to be protected if it's not actually going to use its band. Now, there are things like public safety that you do want to protect anyway, and for those you need to do something different. Give them a beacon that sends everybody out of the band. Do something. Jail system can't actually protect them. Okay, so rarely active primaries are our hardest cases. Let's look at some performance metrics. We saw before, you need this minimum PTX that you're going to protect, which means that one of your performance metrics has got to be these average primary collisions. These primaries that are not actually going to be protected. So you can think of this as your minimum protected primary. Here is your average band utilization. And this is going to depend on whether that secondary is in the home band and whether that secondary is wrongfully in jail. So the more primaries you protect, the less you're going to be able to fill these spectrum holes. And this is going to depend on this wrongful conviction rate, this P wrong. As you get better, you can get more of the band. Now let's look at that directly here. The last one was average over lots of cases. This is one snapshot with one set of parameters. Your probability of transmit is down here, band utilization here. Different colors are as the band being used by different folks. We're protecting all of the primaries that are around more than 20% of the time. If they were by themselves, they would use this here. This blue as well as this red. Honest secondaries, when they're in the band, can capture this green. And they're going to be affected by their sensing cost as well as their wrongful time in jail. All of the black region are cheating secondaries. And it curves because they're spending more time in jail. Now, let's make things get better. We have the cost of sensing and this wrongful conviction rate. As the cost of sensing goes down, you can get more of the band, and then we stop cheating. And as this goes down, there's no longer cheating, no longer collisions. What about this P wrong? To really let folks stay in the band longer with higher PTX, we need to bring that p-wrong down too. And this is all keeping the same sanction, just letting technology improve. The future will be better. Let's look back at that database recovery plot that we saw earlier. This is what the primary can get, or what the primary has, and there are this many primary time slots per database token. This is what a database alone can get. Cost of sensing doesn't really matter for this expansion, so we're just going to look at p-wrong. Spectrum jails can get this and anything underneath it. Let p-wrong get better, you can get all of this too. So the better you make technology, the less it's going to depend on when you're running this enforcement system. Which means that you don't have to run the enforcement system at the same time scale as the spectrum holds. You can make it a little bit slower, and that'll be okay. Okay, great. So we've answered all of our questions. What are our important parameters? To set the sanction, you need it to depend on this minimum protection. Yes?
So just a quick question. So what you wanted was that the transfer cost in the unlicensed band should be smaller than the place where you get caught. But wouldn't this cost depend on what the number of other transmitters transmitting there? So
Yes.
how do you model that?
So we don't model that at all here. What it means is that you're going to have enough unlicensed bands and some means of controlling congestion. What you really do need to do is make sure that you have an unlicensed band that's big enough for everybody. And if that means that as there are more wireless devices, you send more spectrum as unlicensed band. That's what you need to do. But we don't really look at that here. Okay, so now we know what these important parameters are. For the sanction, we need this minimum protected range. We need to know how you catch and the size of the home band. For performance, we need this p-wrong and the sensing cost to go down. Okay, so right now, primaries are treated as victims. They're devices they're networks that were created in isolation with no thought to sharing. But in the future, that's not necessarily going to be true. We can have them also design their new systems to have some provisions for sharing. And the question here is really, should enforcement be one of them? And we're going to model this as a Stackelberg game. So what we want is to put the primary in the position of reporting interference. Because we really want this do no harm rule. And the primary is the one that knows whether harm actually happened. So they're in the perfect position to scream, help me, when there is interference. So we model this as Stackelberg game. Primary is going to move first because it needs to deploy a system with a particular reporting of interference characteristic. And it can assume that the secondary is going to be rational. When that secondary moves second, it'll be able to learn the type of primary it's facing and act accordingly. And this is kind of what we want. We want to know whether the primary has incentive to report interference. Are there any cheating behaviors for the primary, and what do we do about them? And again, performance metrics and what's important. So here's how we're going to walk through this game. Secondary is going to be along this side, primary along the top. Secondary has the same options it had before. So let's start with, does this primary have incentive to report interference? And intuitively, it should, right? It needs to protect itself. So how does that work here? The secondary has the same sanctions it did, or same costs it did before if the primary is reporting. If the primary does not report, it never goes to jail. What are the primary costs? There's some cost of reporting. If the secondary is cheating, there's a cheating cost. It's going to drop a lot of packets. If the secondary is honest, it's going to drop some packets. So there's an honest cost, an honest secondary cost. And the primary is really choosing between these two states with these blue bars, because that's what the secondary would do in response to its choice. And in this case, primary will report, which is great, and exactly what we thought it should be. But notice, this is going to be important, this reporting cost. that reporting cost is really, really big, then it's just going to accept that cheating harm instead of actually doing anything about it. Okay, so it reports the way we want it to. What else can it do? I mean, nobody's really watching the primary, seeing whether it's going to report things correctly, right? I mean, it'll report interference, but maybe it wants to send some reports when there is no interference. This could happen. So we're going to call that crying wolf. If it reports, everything is the same as it was before. If it cries wolf, there's an extra cost for doing that. That's around the size of the reporting cost. And this secondary wrongful sanction gets really, really big. So essentially, if it cries wolf, it can send the secondary to home bend. And in this case, it wants to. But again, notice this reporting cost. What if that reporting cost got bigger? Crying wolf would also be expensive, and the primary would just accept this honest secondary harm. So what are we really saying? There is this harm there. The primary doesn't want it, but there's going to be some harm. We need to decide how much. And controlling this cost of reporting is how we decide how much. And this reporting cost can actually be controlled. I mean, you can think of it even as a mini jail that the primary would have to turn off for a minuscule amount of time whenever it reports something. This could be done. So we can choose what is this minimal acceptable level of harm. And so that's what we do. We set the reporting cost based on this acceptable harm. Sorry, max acceptable harm, not min. So what else will the primary want to do? Again, nobody's really watching this primary. Do you remember this rare primary event that was not so great before? We can't protect these rare primaries. Well, nobody's watching. Primary can transmit more. There's some cost for doing that. But if it transmits more, the sanction will be right, and it can keep the secondary honest. So what is this really saying? This extra transmission, it could just be gibberish. That is a possibility in which it would not be great. But the primary could also use that to hire a band sitter. And this band sitter would come in and use the band for it and make sure that the secondaries are actually watching for it. And this is very interesting because the primary will pay for somebody to use their band, which is kind of backwards from what you would really expect. But they're not paying somebody to use their band, they're paying somebody to figure out how to respect them correctly. So there's a nice incentive structure going on there. So we can have these band setters, important parameters. We can set our sanction based on the same things we had before. This cost of reporting is based on this maximum acceptable harm. And these performance metrics we're not going to actually look at here. They're in the thesis. But just like this band sitter case, the primary has incentive to keep good equilibria. This is not going to fall apart, and bad things are not going to happen. And everything is going to get better as you make things better. So we have a few minutes for this. There's multiple secondaries and aggregate interference. So what is the real problem here? What are we facing? There isn't just one secondary. There are a lot of secondaries, and they're scattered out there somehow. Now, the tech literature and policy literature in spectrum sharing really likes to think of these, this swarm of commutative radios as either being one guy sitting at the edge of this no-talk region, or maybe moving a little bit, or a sea of them. And really, they're completely ignoring the middle region, where you have lots of them, but they're moving around, and there's some risk of interference changing based on where they are. So in my thesis, and we're not going to look at this too much, But we really explored what is this nature of this aggregate interference? When does it depend on one guy, where you get something that is heavy-tailed and looks like this, and when does it depend on lots of them, where you get something that's going to look more Gaussian? And even in the far extreme cases, when there are lots and lots of them, they really do look like just a deterministic value. And once you know what this interference is going to look like, you can start asking questions about what to do about it. Because really, you're worried about this case. All of these multiple secondaries lined up right along the edge of the no-talk region. That's going to be too much interference. And the question is, what do you want to do about this? Do you want to make the no-talk region bigger? Do you want to make them all quieter? Do you want to thin them out somehow? And all of these things are looked at in my thesis. We're not going to go over any of them here. And then once you know what you're actually trying to get, you can think about how to use jails to incentivize that solution instead of dictating it. And we have a really simple way forward with a queuing model, but there's a lot of work left to do in there. Okay, so what has this thesis accomplished? We've built this incentive-based model, which is the first mathematical model of trust in spectrum sharing, that really allows you to have trust and certify trust, and then let performance improve as your devices get better. So this is kind of a before and after. Before, we thought implementation is really hard, and now we know, I mean, we need these pieces anyway. They still might be hard, but we need to do them. And once you have them, you can do something better with them. These architectural requirements, you're really going to need these unlicensed bands and base the sanctions on those. We know that rarely active primaries are the worst case. We can now have this quantitative handle on this trade-off between band utilization and primary protection. And we know what all the important parameters are. For trust, they're really this catching. And for it's all related to catching. And for performance, it's really about be wrong, cost of sensing, honest harm. These performance metrics that should improve in the future. So this is kind of your theory of spectrum jails. And you remember all of these policy questions that we mentioned at the very beginning of the talk. We can say something about those too. With this theory of spectrum jails, we can say something about property rights. We can help define them, define what you're capable of defending, what you're capable of enforcing. And we can think about them differently than what the policy people usually say, which is that you define your property right, and when things go wrong, you start fixing them. You don't have to do that. You can define them and have everything just get better. And this is great. We can say something about this unlicensed versus commons versus markets. We can enforce any of them, but you are going to need that unlicensed band. So it's really important to keep them. This courts versus spectrum tribunals, we can get both of them, the best of both worlds. Something that uses pieces that we already have or need, and it is focused on knowing things about spectrum and doing good things in spectrum. And we can implement both of them in technology. This identity, we know it's important, but now we can give you performance specifications and tell you exactly what this catch needs to be, and it's not actually all that high. Catching 80% of the time is perfectly fine. Be wrong, however, needs to be really low. Your wrongful conviction rate needs to be tiny for performance to actually work. And I didn't talk about this at all here, but in my thesis we also have a discussion of kinds of sanctions and how they work. So we understand properties of jails, which we've used in the rest of the thesis, and fines, which are usually what's used in economics. And these actually operate in very different ways. So that's all in the thesis. So this is kind of my thesis. Where do we go from here? Because this really starts a new area. This is a brand new area of how do you do trust in spectrum sharing. And there's a lot of places to go from here. I mean, we have a lot of technologies that we're going to need for trust. This identity, we don't have identity yet. We need to figure out how to do it. There's some cryptography work to do because you need to be able to, it's important to be able to make this decision to operate only in an unlicensed band and not be subject to jail. This needs to be secured. We don't really know how to do that. In my thesis, we have secondaries that have costs based on delay and energy, but there's also latency in that cost function, and we haven't done that yet. That needs to happen. And this multiple secondary story has been advanced with my thesis and started with my thesis, but there's a lot more work to do. Improving performance is working on this identity and looking at adaptive jails. You can look at other enforcement mechanisms. I mean, jails might not be the actual way to go, but we do have metrics now that any other kind of enforcement will want to use those metrics compared to jail to see what they can actually do. There's a lot of policy work to do. Databases don't enforce right now, and we need to figure out how to give them this kind of ability. And related to that, there's a lot of law work to do. I mean, doing enforcement through technology is kind of some hairy legal ground. And there are some ideas in this. I mean, code is law as a something that Lessig has popularized. But I mean, we're not there yet. Rights for robots might be the way forward. But that needs to be figured out. So that's what we've got. I'd like to thank a few people. All of my collaborators, Rahul, Mubarak, Pulkit, Hari, Girija, Kate, and Francois Michelli, who helped with some of the stochastic geometry stuff. Big thank you to all of my fellow group members, which are all of these folks and Seyan. Two really different things. Big thank you to my committee. Big thank you to all of Wireless Foundations, past, future, present. You guys are great. And of course, big thank you to my advisor, and it's been a pleasure. And thank you all for coming to my talk. There are refreshments downstairs in Wireless Foundations. So thanks. And we actually even have a couple minutes for questions. Yes.
Yeah, you told us in the beginning how much companies paid for the primary license to FCC. How much do they have to pay for secondary licenses? Are there any regulations?
So that's part of this debate of what should future spectrum be allocated to. Right now in the TV bands, it's essentially unlicensed. If you can prove that you'll follow the rules, then you're allowed to go. But the PCAST report opened up the possibility of having licensed secondaries that will have more rights than just an unlicensed user would, and they will certainly have to pay something. But it's unclear how much, and part of that is that there aren't really great business models yet to figure out how to really deploy systems that use these spectrum pools as their primary space, or their expansion space beyond the unlicensed band, really. So it's unclear right now.
First, let me say that the talk was worth the wait.
Thank you.
It seems that a key component of the system is a reliable identity system.
Yes.
Do you have any idea of how this could be done?
So there was some work that Anant did with some folks at Boston University that embedded the identity signal as an on-off characteristic in your transmission. That is certainly one way forward. There's also ways to put in watermarks, or there are a few other examples, but the hope would be to create, or the real problem of identity is to create a signal that is understandable even at low SNR. So it's kind of a Mac channel like problem, not Mac channel. What? Broadcast. Thank you. It's really like a broadcast problem, and broadcast over unknown channels problem. So it's not an easy problem, but there are some architectures that might work and some information theory things to do too in that space. Yes.
So, usually for white space, what parts of the spectrum are actually they are trying to treat as white space? I mean, there are also military bands, right? I mean, are they are going to allow those as white space, or what is the actual
Yes.
white space?
So right now it's TV bands, and the next piece is really the federal spectrum, and that'll be government and military. And the idea would be to have sharing as a way of transitioning these government and military users into more efficient uses. But those are the next ones that are going to be colonized.
So you mentioned that probability of wrong needs to be low as an important factor. So for example, right now, is that limited by sort of how good we can do sensing, and roughly how low is it right now?
So it isn't right now. That's related to this identity problem. P-wrong is an identity parameter. So think of it this way. One way to do identity that would actually work is to say there's interference, all cognitive radios must be quiet. Your P-catch is great, your P-wrong is awful, because it's really going to depend on everybody else. Until we figure out how to do identity better than just kick everybody else out, we don't really know how low that P-wrong can get.
So that means the ability to sense which one of secondary is actually impinging or causing the variance is very difficult.
Yes. But again, P-catch is what you need for trust. P-wrong is for performance. So as we figure that out, it will get better. And I mean, if way in the future you want to is set out a nice monitoring sensor network that is really, really dense and everywhere, then this problem gets a lot easier. You just won't be able to do it at first. And we no longer have the room, so let's move to deserts. Thanks everybody.